Hello, hello, hello. This is Nicholas. I've got really kind of a different video that I wanted to do that I'm pretty excited about. And we are, I'm sure, all familiar with the fact that pi is irrational, right? We've used this fact many, many times throughout our algebraic and maybe in our calculus math careers, if you will. But I don't think very many of you know how to actually prove this fact here that pi is irrational. And so that's what I'm going to do today is I'm going to give a proof that pi is irrational. It's going to be a little a little out there. The first thing I'm going to start with is I'm going to define this function. I'm going to start with a positive integer b. So b is going to be an element of the positive integers, and n is also going to be an element of the set of integers. But n is just going to be a non-negative integer, so in other words, for all n greater than or equal to 0. Okay, and so I'm going to define this function a sub n of b to be, all right, b to the n times the integral from 0 to pi of x to the n times pi minus x to the n times the sine of x all over n factorial dx. Now where I'm coming up with that? Truthfully, the man that came up with this first is by the name of, gotta give him credit, Ivan Nevin, I guess, and he came up with defining this function to begin with. So now the integrands, in other words, what we're integrating from, this is definite integral, are from 0 to pi of this wacky function right here. And so now what I can do is I know that whenever I actually do this integration, sine of x is always positive from 0 to pi. And so likewise, x is going to be a positive number going from 0 to pi, as is pi minus x. And so what this tells us is that for all n comma b, so for all n and b, a sub n of b is always going to be greater than 0. And in addition, this, if we consider x times pi minus x, so in other words, this part here, just getting rid of the exponents here, maybe you know this, maybe you don't, but this is guaranteed to be less than pi over 2 quantity squared. The reason why that is, and this is true in general, if I'm taking two numbers and I'm multiplying them together, the idea is that like let's say I've got 1 and 3, and I imagine a number line here. Let's imagine a number line. Let's just think about this in general. So I've got x and then like pi minus x, and then so pi over 2 would be their arithmetic mean. And so if I take the arithmetic mean is always greater than or equal to the geometric mean. That's the AMGM inequality. So the arithmetic mean is greater than or equal to the geometric mean. So now what I can do is I know that the geometric mean, it would technically be x times pi minus x, and I take the square root of that. That's the geometric mean. But and then also the arithmetic mean of those numbers would just be pi over 2. But if this is true, if this arithmetic mean is greater than the geometric mean, then the square of both of those is true as well. And so in other words, what that tells me is that pi over 2 quantity squared has to be greater than or equal to x times pi minus x by the AMGM inequality. And I've given a proof for that for this specific case for the two two numbers or two entries case. Later on, I'll do a more general proof using Lagrange multipliers, but that's why that statement there that I've made is true. So what we can do is we can write the following. So what I'm going to do now is I'm going to note that when I actually do the anti-differentiation, I'm going to note that a sub n of b is got to be greater than or equal to. Now we have, I'm going to replace the x to the n times pi minus x to the n with just a pi over 2 to the 2n. And then what I'm going to do is I'm going to keep my n factorial that I have on the denominator. And then the sine of x, what I can say is that that's going to be at most 1, which is less than pi. So then what I can write for the sine of x is I can write that a sub n of b has got to be less than or equal to pi, this pi coming from the sine of x here, pi times b to the n over n factorial. And then I'm going to take this here and then replace that with pi over 2 to the 2n. And then some algebra happens, and we would get pi times b pi squared over 4 to the n, all over n factorial. And now, if I have a sufficiently large n, so in other words, as n gets bigger and bigger, sufficiently large n, then hopefully this is, I can explain this one of two ways. The first way I'll explain it is that by Stirling's approximation formula for n factorial, that a sub n of b has got to be less than 1, because this n factorial is going to grow quicker as n increases without bounds compared to the nth power in the numerator. And the reason why that is because this here is just a constant multiplied by itself n times. This here is it's n things being multiplied together, but you're going to have numbers greater than this b pi squared over 4 being multiplied in this n factorial. And then when you multiply bigger and bigger numbers together, the denominator here is going to get bigger. It's going to get bigger quicker. And it might just be best to remember, or maybe you haven't heard of Stirling's approximation formula. So I'll give that to you now. If we have Stirling's approximation formula, that's going to be that n factorial is going to be approximately equal to, because it is just an approximation, square root of 2 pi n times n over e to the n. And so now this is an approximation that gets better and better as you get bigger and bigger n. So now what I can do is I could imagine substituting in n factorial for this square root 2 pi n over e to the n. And then as n gets bigger and bigger, the exponents here, so I would plug this n factorial into here for all of this. And then I'm going to have my exponents of n kind of canceling out, if you will. And so what I'm all trying to get across here is that for sufficiently large n, the a sub n of b is going to be between 0 and 1. So that's what I'm going to write here. So now it's going to be always less than 1 as well, since the factorial grows quicker. So 0 is less than or equal to a sub n of b, which is less than or equal to 1. And we're going to circle this because it's going to be an important result later on. Now, here comes kind of the contradiction step. So now we're going to assume that pi can be a rational number. So pi is of the form a over b for the greatest common denominator of a comma b being 1. In other words, a and b share no prime factors. In other words, they're relatively prime. So now I'm going to define this function. I'm going to define f of x. I'm going to define it to be x to the n times a minus bx to the n over n factorial. And so where did I get that from? Well, remember, if pi is equal to a over b, so now the a and the b are coming from, look at my laser here. The a and the b come from right here. I'm getting this function from. And so basically what if you look at this function here, and you look at this function here, and you compare the two, then you would see that a would be pi and b would be 1. So I haven't really done anything crazy here. So, and also just to keep in the back of our minds, this could also be written as ax minus bx squared to the n over n factorial. Now, since a is 1 and b is, or since a is pi and b is 1, then a sub n of b could be equivalently written as the integral from 0 to pi of this f of x times the sine of x dx. Okay? Yeah. So, now what I can do is I can do some integration by parts on this. I'm going to do 2n plus 1 integration by parts. And so when I do this integration by parts, I'll get negative f of x cosine of theta, because the integral of sine gives me a negative cosine, and that's going to be evaluated from 0 to pi. And then we're going to have alternating plus and minus signs. So then we have a minus, and then the integral of the cosine will give us a the negative sign. So we will have minus negative f of x times the sine of x evaluated from 0 to pi. Another way you might think of this is if I have di and I differentiate sine x, because that's really what I'm doing here. I get cosine x, right? And then I integrate, or I'm sorry, my bad. My differentiation part will be the actual function itself. So this should be a f prime of x, my bad. So I took f of x, differentiate it, and we're assuming it's differentiable, and it should be, right, as long as n is not 0. And so now I integrated sine of x, and when you integrate sine of x, you get negative cosine of x. We have a plus and then we have a minus, and so that gives us a negative right here, and then we have a negative of a negative right there, and so this is what we get. Now we're going to have a plus because the signs alternate, right? And that's just, I'm just going to write dot, dot, dot. And then now I'm going to write plus or minus for here. You'll see why, because this term I'm going to have it be f2n of x. So the 2nth derivative of f evaluated at x times the cosine of x, because for every other one of these we would get a cosine, and every other, like, see, we're starting with a cosine, and so then we'd have a sine. Then the next term here, if I wrote it, we would have a cosine and then a sine. So every see, this is really like, you can think of this as like the 0th derivative. And so every two derivatives of this function will get a cosine, and every odd derivative of the function will get a sine. So plus or minus f 2n of x, cosine of x, and that's evaluated from 0 to pi as well. And then now I'll have a plus or minus again, and I'm having the plus or minus because it would depend upon whether n is even or odd here. So I'm just writing plus or minus for now. And that's going to be the integral from 0 to pi times, or of f2n plus 1 of x, so the 2n plus 1th derivative of x, times, now we will be using this same thing here since we're not integrating it once more, so we'll still have a cosine of x dx. Okay, so hopefully what I did there with the integration by parts kind of general made sense to you. So now if we have some k between 1 and n, so for all k being between 1 and n, f sub or the nth derivative of f evaluated at x is going to be 0 at x equals 0 and x equals pi. Right? Because each time I differentiate this n times, I'm going to have a factor of x in there, and so whenever I plug in 0, I would get 0, and then whenever I plug in pi, since this a here is a pi, I'd have a pi minus, and then this b here was 1, so I'd have a pi minus a pi to whatever power, and so that would again give me a 0, and then the whole thing would be 0. So the derivative there would be 0. And now if we have for all n, or I'm sorry, for all, call it k because we're already using n. So for all k between, now we're going to consider n plus 1 to 2n, f sub, I should have wrote f sub k, or f, the kth derivative of x. Here, though, we have f sub k of x, or f, it's not a sub because it's f super of k, f super k of x, the kth derivative of f evaluated at x is, see, now we've taken care of all of these factors here with the product rule, but now we're going to have a bunch of other factors from the product rule, and so we would actually get another n factors of x, right? Because we have this x and this x, and so when we multiply them together, we're gonna get double the factors of x when we use the product rule, since there's two parts to the product rule. So basically, what I'm saying is that here we're now going to have this kth derivative of f evaluated at x is going to just take on integer values. So integer values, just different integer values. We don't know what they are, and we don't really care. And the integer values will be when we let x equal 0, comma x being equal to pi, because we're going to have all these extra factors when we do the product rule and we take this derivative. But then this x to the n here is no longer there. But we're going to have a bunch of other stuff. It's going to get really complicated. Now, the third case here, we go up to the 2n plus 1th derivative. And notice that the 2n plus 1th derivative, that will eventually be 0, because once after the 2nth derivative, there will be no more factors of x that we will have, right? At the 2nth derivative, we'll get rid of that last factor of x, and we'll just have a constant. And so then when we differentiate that constant, it becomes 0. And then the whole thing just goes to 0 because we're multiplying it together. So in other words, this integral here will just be 0. It'll just go away. So I'll put this in red. We don't need to worry about it. So what I'm getting out of all of this is that, so these here, these from the derivatives from 0 to n, those are going to all be 0, so we can get rid of those. And then all of this that I didn't write from n plus 1 to 2n derivatives, those will be, I'll write it actually in red here, those will all be integers, right? So basically what we're getting out of all of this is that all of this implies that under the assumption that pi is irrational, not irrational, that pi is a rational number, in other words, of the form a over b. If we assume that to be true, then that implies that a sub n of b is always going to be an integer. But that is nonsense, right? Because look at this and look at that, right? So here we have taken a sub n of b, we've shown it to be between 0 and 1 by just kind of looking at the factorial, and you could also look at it rigorously with the Stirlings Approximation Formula. But then if we make this assumption, then we get this contradiction right here. And so therefore, our assumption that pi was a rational number is wrong, and so therefore pi is irrational. I hope you were able to follow through all that and see kind of the beauty in what I've proven here. And I hope that this proof has made sense to you. This is probably the shortest and most elegant one I could find. And I think I explained it relatively well, although it is me, so I understand what I'm saying. But hopefully you do too. Anyway, I think that wraps it up for this video. And I probably should have done this proof on March 14th. But it's May.